So let's talk about the math. The math is usually easier. It's the sum over all values of our input sequence of e raised to the minus j omega n. And so this is a complex result. It's just a function of omega. There's no n in the DTFT. It's just of omega. Just like in the time domain, it's just of n. There's no frequency in there. And this is a continuous function in omega, unlike your input sequence, which is real and a discrete function of n. You can go backwards too and recover your x of n from your DTFT. It's an integral since your DTFT is continuous. And this is everything that you need to know. This is everything there is to know about the DTFT from a mathematical standpoint. Now, this top version is used all the time. The bottom version is never used. Much like we talked about in continuous time in signals and systems, that the forward version of the Fourier transform was often computed, but if you had to go in reverse, you'd use tables and transforms. And that's the same thing we're going to do in discrete time. So far I've just talked about the intuition, the magnitude of the DTFT. I haven't talked about what the phase relationship is. And just like we could graph the magnitude, I could also graph the phase of the DTF. The phase is obviously going to be uniquely limited to minus pi to plus pi. Oftentimes, we really don't care about how the signal looks in the time domain. We care about where its frequencies are. If you are interested in creating a high-pass filter or a low-pass filter for music, maybe you want to emphasize the bass beats. You really don't care about what the phase response is much. You care about what the magnitude is. You want to see that your filter lets through these low frequencies over here and cuts down these high frequencies. If you're interested in quickly scanning the stock market to see if there's any underlying strong frequencies that you can exploit and earn money from, you really don't care about the phase at first. You're just scanning to see if there's any peaks in this magnitude domain. Because if there's a big peak that you see at a magnitude of high over 16, you can zero in on that and then figure out when to buy and sell. The phase is the offset for a particular frequency in the time domain. So the phase becomes important if you care about the way the signal actually looks. For the stock market example, you look through 1,000 different stocks, look to see if any have a strong component in their magnitude. And then once you see one that has the strongest component in the magnitude, zero in on that and ask what's the corresponding phase. That phase will tell you when to buy and sell. The magnitude, the frequency at that magnitude spike will tell you if there's a cyclic relationship at pi over 16 omega, which corresponds to, once you know the sampling frequency, corresponds to maybe every 5 days. And then the phase will tell you when the high and the low peak is to buy and sell. All right. That was a very rough intuitive thing. If you were to graph that phase, people typically graph that phase. Remember, we're graphing it versus frequency. So we only need to graph it between 0 and pi. And then the angle doesn't really make sense beyond that region of negative pi to pi, right? Because if you're graphing that angle, once that angle gets to be greater, here's your theta in radians, once that angle gets to be greater than pi radians, you can just as well represent it by a negative pi radians. You might see something that looks like this. So something might have a strongly increasing phase versus frequency. And of course, the way that you'd actually see it plotted, because you can only get a unique number between plus and minus 180, is that it would look like it goes up like this, and then it would suddenly go down to negative pi and then continue up on that same upward angle trajectory. Because there's no difference between something that's at 181 degrees and something that's at negative 179 degrees. Questions on all of that? That was a lot. MATLAB compensates for this. If you ask MATLAB to tell you what your angle is, it will give you something like like this, because it doesn't know if it finds an angle at a particular frequency of 181 degrees, it doesn't know that it's 181 degrees. It's going to kick it down to minus 179. So in MATLAB, instead of plotting your omega versus your angle of capital X, so here your capital X is your DTFT. We've somehow computed it already. I'll show you how to compute it in a minute. But instead of computing this, which will give you the red waveform that just keeps on going, which will give you the blue waveform, which will be limited to negative pi to pi, there's a new command called unwrap angle X. 1, 2, 3. And what that will do is, instead of plotting given this kind of data in, it will see if you were at 179 here, 180, then if it's minus 179, unwrap will realize that that's really just a continuation of what was just before at 179, and it will give you this nice red line that goes straight up, which is intuitively more reasonable for what a angle response might look like.